All right, and now it comes another important detail, or indeed a quite useful detail about polynomials that it really deserves our attention here, so that when you learn and master and become fluent with this skill, particularly at the end of your pre-calculus level course, then when you are going to calculus, then this skill will become very vital for your calculus course. It will be a huge plus for your work at the calculus course later on. Okay, it seems like I really want to promote my students into going to calculus course, but that's the whole point of this course that you are currently taking. It's called a pre-calculus course. It gives you all that prepping, that necessary prepping. It teaches you and it brings all the algebraic experience to your own math learning experience, so that you can carry all of that into your calculus course. Okay, we've learned all of the technique that in your elementary courses you haven't learned that. You only learn the theories, the basic stuff, and then here we're gonna combine all that into the skills. So right after we've learned about finding zeros or horizontal intercepts of any polynomial, let me now take you into looking at how about as far as an actual title of the discussion. Let's look at that. Let's look at what's so-called a polynomial. Okay, polynomial inequality. Okay, but really I feel very reluctant to keep mentioning too many titles. So polynomial inequality. What exactly am I talking about in terms of polynomial inequality? So here's the idea. Yes, just like you have an x squared minus 2x plus 1, for example. I made my polynomial a little too special. How about an x squared minus 7x, okay, plus 12 right here. It's a polynomial. Okay. And then being a polynomial inequality means we want to solve the following. Our goal here is to solve the following inequality. X squared minus 7x plus 12 here. We want to solve for that to be greater than or to 0, for example. That's one quick little example. Or we want to solve for the x squared minus 7x plus 12 to be less than or equal to 0. And then there could be equal sign coming along with these inequality symbols like that. Okay, so that's what it means by we are working on a polynomial inequality. What we are solving here is a polynomial inequality. Why is that? Because once we have put all terms on one side right here, it is a polynomial. It is a polynomial. Okay? Seems like a lot of work waiting for us. But now, believe me, you have had all of that experience. Now it's just the right time to bring all of that learning experience and put them into the right track to handle this kind of problem particularly. So I usually teach this as a consequence of after you have learned about finding zeros of your polynomial. Okay, so now with these quick little ones, okay, this is a polynomial. Let's say if we want to solve for p being like earlier, like I wrote on the board right there, and now I erase that to write it in a shorter form. We want to solve for p being less than 0, for example. Okay, let me bring up the graph. All right, so in my graphing space here with decimals, and there's no need to show the complete view of the browser, so I'll just hide it away and only show the graphing space here. So x squared minus 7x plus 12. Okay, and again, I want you to use your own experience in finding the zeros of this polynomial. So at this point, I want viewers, whoever learned from this lesson here, to look at to quickly find the zeros of this polynomial, because you have already done it. Okay, so now x squared minus 7x plus 12, now on the graph, has the following zeros. Here's the graph of the x squared minus 7x plus 12. So we have 2 zeros. Okay, and so now if we're looking closer, so in the way how this graph is, and it's not the same for every graph of the polynomial, but now there has to be some intervals of the graph. Some interval of the graph falls below the x-axis, and some interval of the graph falls above the x-axis. And those intervals switch between those zeros that we found. Okay, so again, let's look right here at the graph. See, some intervals falls below the x-axis, and some other intervals stays. Some intervals the graph stays above the x-axis. That's what I meant. And so now here specifically, I want to find out x values satisfying the polynomial being less than 0. So less than 0 here means, so this is the graph in red, okay, and less than 0 here means we want to find the portion, the interval where the function, the polynomial here graphically falls below the x-axis, because the x-axis is the line y equals 0 right here. Okay, and so now in that way, graphically we can estimate that, well, we have two zeros estimated from the graph here, that's one at 3 and one is at 4. Okay, and so now right here in the picture, that is the only interval where p of x falls below the x-axis. Okay, so now this is what I'm saying right now, and I'm not saying this is the best solution yet, but at least from graphically, okay, so graphically concluding it, we're looking at for x being anywhere. So this symbol here means x is being inside. It's a sideways cup with a little dash in the middle. So for all of those x values you've seen on the interval earlier, for all of those x values being inside of the interval anywhere between 3 and 4. Okay, and now it has to be a strict interval. Okay, because we want to be strictly down below. Because when x equals 3 and x equals 4, our polynomial here equals 0. So that's not what we're looking for. And so the interval here has to be strictly between 3 and 4 right there. But see, so graphically, this is what we already estimate through the graph right there. But now, what if we don't always have the graphing utilities? And as a matter of fact, it's the technique I want you to learn here. I want my students learning in this video lesson to learn is that technique that even without the graph, we can still find. So I was only using the graph to explain what it means by being less than 0 for a polynomial or being above 0 for a polynomial, because there will be those intervals where the graph of the polynomial stays above the x-axis, or there are other intervals where the graph of the polynomial stays below the x-axis. But then we don't want to give the solution graphically. We don't want to use the graph or rely on the graph all the times to come up with a solution. Because again, anytime looking at the graph, it's only an estimate. We want to come up with a solid, precise technique like that. Okay, and so now to solve for this polynomial. So now I'm going to work completely without a graph. Okay, I use the graph just to estimate the idea like that. So now I asked viewers, when I was writing this down, I asked viewers and students of mine to quickly determine the zeros of this. Okay, and so one way of doing that, we have to go through and see in my lecture where I talked about how to find zeros of a polynomial. I specifically mentioned that we use the factoring technique. The factoring method is to be the universal methods for solving any polynomial for 0. So we're gonna start out as first big step is to put our polynomial in factor form. So in factor form, our polynomial is f of x, p of x equals x minus 3 times x minus 4. So now you are, for this particular little demo problem, you have already seen the graphs before. So this factoring form right here is consistent with the graph we've seen earlier. Okay, so these are the two zeros we found. So the zeros here, all right, the zeros here are at x equals 3 and x equals 4. And once you put your polynomial successfully in factor form, you can never go wrong with the number of zeros, because we've even had that theorem back in the lecture when I was showing you to find zeros. We had that theorem, quite powerful theorem that make that connection between factor of a polynomial and how it becomes a 0. So now we factor this polynomial into two separate factors. So we have to end up with two zeros here. each one of these come out with multiplicity 1 or whatsoever we want to say it. Okay, so now that's zeros. Okay, those are the zeros because once again, because p of x equals 0 at x equals 3 and x equals 4. That's why I call it 0. Okay, so now on my other board, now I'm going to show you this technique right here, because 0 we found earlier was just only zeros. Okay, that's where the graph crosses with the x-axis. But see, crossing or intercepting the x-axis, the horizontal axis, is not going below the x-axis or not going above the x-axis. Okay, so in that way we want to use the zeros, and from where we have the zeros we're going to detect the intervals where the graph stays completely below or stay completely above. So here we're specifically looking for below, because that's what the problem here initially wants. The problem here wants us to find the x values. We want to solve for the x values where our polynomial stays strictly below the x-axis. Okay, so now below or above the x-axis, generally we have one technique right here that we can solve it all. So I'm going to introduce what's so-called the Sine Charge method, or the Sine Charge technique. Okay, we're going to construct what's so-called a Sine Charge, and here's the idea of the Sine Charge. Okay, again, keep in mind your polynomial that we're working with here is currently in factorial form, is already in factorial form. P of x is in factorial form, x minus 3 times x minus 4. That's factorial form, and because of that factorial form we already identified the zeros. So now we had 2 zeros, we had 4 zeros. Doesn't matter how many zeros we have. Let's put a comprehensive list. Let's list all of those zeros on the line of numbers. So this is my line of numbers right here. So I'm going to put all of those zeros we have found on this line of numbers, certainly in increasing order from the left to the right. So again, put all of the zeros on the line of number from the left to the right increasingly. So that means between my 2 zeros I've found, and really where do I put the 3 on this line of numbers? Anywhere. And where do I put the 4? Somewhere that makes sense to the right hand side of x equals 3. So x equals 3 is here, x equals 4 is here. These are the zeros I put on the line of numbers. But now look at the way how it is right now. Look at the way how it is. This line represents the line of numbers. So after putting down all of our zeros, it's going to break our entire line of numbers into, well, in this case, 3 separate intervals. 3 separate intervals. Okay? 3 separate intervals. So now right there from the 3 separate intervals, right now it's just a line of numbers, and we put down, like as I said, we put down all of our zeros here. In this case, only 2 zeros. So we ended up with 3 separate intervals. Right through that, I'm going to draw and create columns, and that's why we call it a Sine Charge. Okay, so this is what I want to do right now. So this now means it's an interval, so that it represents x anywhere strictly between 3 and 4. This is that space in between 3 and 4. It's represent all the x values in between 3 and 4. This interval right here means it's anywhere x greater than 4. And this is, of course, x equals 4 right here at that spot where I put the dotted line. Okay, and then right here, it means x equals 3 right there. And then in this space right here, in this interval, it means x being less than 3 strictly. All right, and so now I am going to do the following. On each interval here, I'm going to check the sign, and that's why it's called Sine Charge. I'm going to check the sign. So this is how I'm doing it. Okay, so I'm going to pick a value. It doesn't have to be, the only thing is each interval you're going to pick a value that falls inside of that current interval you're at. Okay, so say for example in the first interval here, it's an interval that x less than 3. Let's pick a value of x less than 3. 2 works, x equals 1 works, x equals 0 works, any negative number works, because all we need is a number less than 1. I mean less than 3. Okay, so now I can just pick a value, let's call that 2 right here. Pick 2. This is a value that we picked. Okay, we picked x equals 2. So now I am going to substitute this selected value. Remember, we picked this value simply because it's less than 3 and it's in this interval. And whatever happens to this value right here, after we evaluate that, it's going to represent other values as long as the value is inside of this interval. So now here's the idea of the sign chart. I'm going to substitute x equal 2 into this factor form. And the factor form is making it easy for the calculation. 2 minus 3 allow me to write the 2 here in red ink because it's a value that we selected, and we substitute that in our factor form of the p of x. So 2 minus 3 in product with 2 minus 4. We picked this value simply because it's a value less than this is 3 right there. And why is it less than that? Why do we have to pick value less than 3? Because this interval is the interval of all the x values less than 3. This is the whole interval. And like I said, I picked 2. You can pick 1. Somebody else can pick 0. Somebody else can pick 2.5. As long as the number you picked is a number less than 3. All right. And so now I picked 2. So now 2 minus 3 is a negative 1, but negative sign. 2 minus 4 is a negative 2, negative sign again. See, I didn't even worry about putting down the actual value, but what I care is the sign. This is why it's called a sign chart or a sign check right there. All right. So now once I substituted that chosen value into my sign chart right here, then so negative 1, this factor gives me a negative. This factor gives me another negative. So negative times negative, I ended up with an overall positive. All right, so now it's this positive here tells me that in this interval for x less than 3, my polynomial, because the polynomial is the product of these two factors right here, the polynomial has to be positive in this interval. That's how it is. Okay, let's do that again. And the sign check will never go wrong for any problem. Okay, let's look at the middle interval. This time for this middle interval, the value that you pick has to be anywhere greater than 3 but less than 4, anywhere between 3 and 4. Well, we are forced down to pick a decimal, like x equals a 3.5. It all works. Okay, x equals 3.5. That's the value I picked. You can pick a 3.75, you can pick a 3.99. It's all between. Okay, so this is how I see it. In this interval, substituting the value we picked into the polynomial. Here I'm looking at 3.5 and 3.5 minus 3 but minus 4. Okay, 3.5 minus 3 is positive. That factor is positive. Of course, it's positive 0.5, but I don't need to worry about the 0.5. I'm interested in the sign of that factor. Here I was particularly interested in the sign of each factor. All right, so 3.5 minus 4. Of course, anyone knows it's negative 0.5, but I was interested in minus sign, the sign of that factor, the sign of this factor. So now the sign of the overall product, the sign of the overall product is a negative sign. All right, so that now tells me as a conclusion, in this interval, this is one thing I know. In this interval, my polynomial will be less than 0. All right, and so now you will start picking up pace. I will start picking up pace, and you already see where I'm going with this. That interval over here, now you can pick a value on your own choice here. I picked x equals 5, for example. Okay, it's just a value we chose. And now let's test it in our polynomial. Test for the sign on each factor. So we have 5 minus 3 times 5 minus 4. Okay. This first factor gives me a positive sign factor. This next factor gives me a positive sign factor again. Okay, so positive times a positive, we know since long ago, it's going to have to give us a positive sign product right there. So that tells me that if we pick a value, if we have an x value greater than 4 in this problem right here, then our polynomial will turn out a positive. All right, so now the answer is here. The answer is here. The question was asking us to find all of those x values where p of x is less than 0. Where p of x is less than 0. Okay, so now this is what the reason I said the answer is here. This is that interval that satisfies our question right there. Our required work right there. We wanted p of x being less than 0. So where did we find that? The tables tear it down to all detail right there. The only interval where p of x is less than 0 is this interval between 3 and 4. That's why. So now completely without the graph, using the table, I found the answer. All right. So now, I don't think I need this anymore. So now to find that, right, that leads to our solution. In interval notation, So now that's why I was writing this earlier. X is in any x value in this interval, strictly between 3 and 4. And I was talking about the interval strictly inside of that. That's why it's this parentheses. We've got one problem done. So this problem of mine demonstrated the idea. And now I'm going to start getting you into some actual example. And along the example, we're gonna just recognize some more details. But any of the details we are about to learn is just minor details right there. Okay, but the main core idea you have learned that already throughout this demonstration example right there. Okay, and so now even though it's continuing with that topic on the polynomials, but I would like to treat this as a separate discussion on its own right here. So allow me to restart my example numbers. So here, let's call it example 1. Right in this business, the polynomial inequality, because this skill, you will see it again in your calculus courses, in your Calc 1, your Calc 2, we all have this skill right here. Okay. And now before I'm moving to the board and get ready for the example, see one more time back on the graph. See, the graph is showing things that is perfectly consistent with our results we have found. See, anywhere between 3 and 4 is where we have our polynomial sinking below the x-axis. All right. And so now let's look at our first example. Let's look at our example 1 right here. Right, so we would like to solve the following polynomial inequality. All right, so the first one given here. So how about x minus 1 all cubed times x minus 2, okay, greater than, how about or equal 0. Okay, so first of all, it's an inequality. Okay, and the reason I call it polynomial, because aside from that side having the 0, the other side here is a polynomial. So it's an inequality. One side is a polynomial, the other side is a 0. And we want to find out, so what values, I'm talking about what values, it has to be at least one entire interval. It can no longer be individual distinct values anymore. Okay, that's the whole nature of solving for an inequality. So what interval or what intervals of x satisfy this polynomial on the left hand side greater than or equal to 0? we definitely don't want to use the graph anymore. Okay, let's put the graph away. I'm not going to swing back to the graph. I'm only going to use the graph once we're all done, and just use the graph to confirm our result right there. Okay, so now, good thing, the polynomial here is already in factor form. Okay, so let's just, so right now, this step right here, I write it down, but really the students are not really expected to write this down. It's just, I just want to make it clear that the polynomial we're looking at is the polynomial that's already in factor form. Okay, that's our polynomial right there. Everything on the left-hand side. Good thing it's already in factor form. And so now we got a couple multiplicities here. I mean, we got that multiplicity 3 and a multiplicity 1 on that 0, x equals 1, and that other 0, x equals 2. So as far as the 0, we found 2 zeros. X equals 1 and x equals 2. Degree of the polynomial, not important in this problem right there, but we have found in factor form here, we immediately know that we have two zeros here. One of them is x equals 1, the other one is x equals 2. Okay, and we want to find all of the intervals that satisfy, interval of x that satisfy the polynomial here greater than or equal to 0. Okay, so that's enough. Let's get to work. I'm going to just use this narrow space here to write down the final answer, but the main work is going to be over there. All right, so once we have put our polynomial in factor form, so at this point you have to understand, and after learning about how you find zeros of a polynomial, that skill is how you can put your polynomial in factor form is extremely important. Okay, you keep working at that skill even though there's no clear instruction, there's no clear how-to instruction about how to factor your polynomial. It's still such an art out there. Okay, so now this polynomial, we already had that in factor form. So now just to construct the Sine chart right here, the first step I'm doing in the Sine chart, all right, I'm going to think about, first of all, the line of numbers. And then on this line of numbers, I'm going to list down all of my zeros that I found from the other board. Put all of them on this line of numbers, increasingly from the left to the right. So in increasing order from the left to the right. So that means x equals 1 is here, and x equals 2 is here. All right, so what that means now is that in between here, this is the interval where x is less than 2 and greater than 1. It's an interval already. Okay, and then this interval here means x is strictly greater than 2, and this interval means some x value less than 1. That's how it is. Easy enough for anyone to catch. And then from this point on, I'm going to draw the chart just like that. So from a line of numbers, now I'm going to create that. I'm going to put that into a chart. So now I'm going to pick values. We're going to pick values in all three intervals right here, in all three sub-intervals. So this one here, I'm going to pick x equals 0. Because all I need is a value less than 1. And again, I believe I mentioned this earlier in the video lecture here. But let me emphasize again, we definitely don't want to pick any one of these two numbers, x equals 1 or x equals 2. Because that's doing nothing good. It's going to make your polynomial equal zeros. Because these are zeros of our polynomial. So we're going to have to pick values in between these zeros. Okay, so I picked x equals 0. You can also have your choice to pick x equals -1 or positive 0.5 or anything like that. But as long as your value is less than 1, that's good to go for this interval. That's good to go as a selection for that interval. Okay, so that's my choice. You can have a different choice as well. But now to get this work, I'm going to substitute this into my, so let's remind ourselves about the interval here. The polynomial here. The polynomial we're looking at here, and that's the reason why I wrote it down on the other board right there. The polynomial, I wrote it down, even though I said, students are not required to, but even an instructor like me who has done this for years, I still prefer to write it down to make things so clear. Okay, to document every single one of my steps right there. Okay, so P of x is that factor in product, is that polynomial in factor form. Okay, so So now I have p of x equals this x minus 1 all cubed times this x minus 2. All right, so that means now when I substitute 0 into my polynomial, it's completely a trial thing. We picked a value, we know for sure the value is in this interval less than 1, and then once we pick that value and substitute that into the actual polynomial, whichever the sign that comes out, it's represent the sign of the polynomial for the entire, and that's what this zone of the sign chart is for. We want to indicate the sign calculation, the sign expectation of our polynomial. Okay, so now I'm going to have to switch between black pen and red pen right here. So this is cube, and this is just power 1, but I'm looking at 0 minus 1, but raised to the third power, and then in product with 0 minus 2. See, because I substituted my selected value, my chosen value, into the product form, okay, the factor form of my polynomial. So now it has a just little extra experience compared to the earlier demonstration problem that we've done right there. But so 0 minus 1 by itself is already a negative sign. So it's a negative 1, but we raise it to the third power. So how about just let me write the sign only, the negative sign, but raised to the third power. And then this 0 minus 2 gives me another negative factor. So negative factor raised to the third power and multiply with another negative factor. So really, what does that tell us as the overall final sign of the entire product? It has to be a positive one here. All right, so the one I wrote in red is the final sign of the entire polynomial after multiplying all these together. Okay, so that means the polynomial p of x, okay, is going to be positive, see, strictly inside of this interval, anywhere less than 1, anywhere x less than 1. Okay, what about the one in the middle here? I'm going to pick, so between x, between 1 and 2 here, between 1 and 2, I can go with x equals 1.5. We have to go with decimals sometimes. Okay, so now again, I'm going to produce two separate factors like that. One of them is being cubed, but here I'm looking at 1.5 and 1.5 again. This is 1.5 minus 1, and then there's a 1.5 minus 2. Okay, so 1.5 minus 1 is a positive factor. Okay, 1.5 minus 1 is a positive factor, and then we're going to raise that to the third power because it's greater than 1, so 1.5 minus 1, and your calculator can verify that for you. Okay, and then 1.5 minus 2 has to be a negative factor. So positive factor and raised to the third power, but multiply with a negative factor. Your overall sign here at the end product has to be negative. So in this interval, our polynomial p of x must be, doesn't matter if it's any other value. Here I chose 1.5. Any other values, for any other value, as long as it's between 1 and 2, the polynomial will be negative in that interval. Okay, negative in that interval. All right, so now let's move on to the last interval. Okay, so now when x is greater than 2, let's pick a value. How about x equals 3? Okay, I picked that. You can pick x equals 4 or anything else as long as the value is above 2. So now, again, in my factor form, the first factor is 3 minus 1, and then raised to the cube power. And then the next factor is 3 minus 2. Okay, and so now let's check for the sign. The first factor before that cube is going to give me a positive sign because 3 is greater than 1. So 3 minus 1 is a positive factor, and then raised to the third power. And then 3 minus 2 is another positive factor. Okay, it has power 1. So now it's all going to be positive. So my final sign here is a positive sign. That means this red plus here means my polynomial outputs value in the entire interval here, x greater than 2, has to be a positive interval. All right, so now we have found our answer. So the chart is here. allow me to swing to the other board and categorize our answer and formalize our answer. This time, in order to satisfy greater than 0, we have spotted two separate intervals. One of them is that interval being less than 1. The other one is the interval being greater than 1. I mean greater than 2 right here. The other interval is the interval where it's x greater than 2. All right, so now in that way, here's how I'm expressing my answer. So now just here's the logic right here. See, don't worry about the equal sign yet, okay? At least the bigger part of this inequality is the part where it's positive. Okay, so now I'm gonna write x being inside from the left to the right. The first interval we saw in the sine chart was from anywhere from -infinity to 1. Okay, infinity will always get the negative. We'll always get parentheses. I'm leaving that a little open here. I will get back to that and enhance that later. So right now it's not my final answer, but at least I'm seeing strictly between this interval we have the functions being positive. Okay, we found another interval from 2, anywhere between 2 and positive infinity. Another interval, because those are here. Those are where our p of x is greater than 0. So less than 1, greater than 2. Okay, these are the intervals where we met our requirements. The polynomial has value above 0. Okay, that's why I came up with this. And so now we put unions between the two separate intervals. All right, but sadly we're not quite done, because this inequality indeed has an equal sign attached to it. That means we also want to include the values of x causing the left-hand side equal 0. Include, like I said, include. Okay, so include. So that means in this chart right here, I am going to include 1. In this interval, I am going to include 1. In this interval, I am going to include 2, because those are 1 and 2, x equals 1 and x equals 2, they were your zeros. They are the x values that caused your polynomial to equal 0. So now I want to include my x equals 1 in this interval. And I want to include my x equals 2, I'm using that term right there. I'm including x equals 2 in this interval. So in that way, now I'm going to adjust my interval. So here's how I'm adjusting my interval. So this left end will never be brackets because it's infinity. But this end right here, now we know that we're including x equals 1. So it becomes brackets there. All right, and now with that interval right there, I know on the infinity end, it should never be brackets. It's parentheses only. But this left end right here, I argued earlier that we can include 2, x equals 2. So now I'm going to change that to brackets. Now, ladies and gentlemen, this is my final answer. Okay, I'm finding the intervals that satisfy this left-hand side inequality greater than or equal to 0. All right, so that's how we solve a problem like that. Let's go ahead and solve another one. Okay. All right, so as part B of our example, let's look at let's solve x plus 2 squared times x minus 3. Okay, and how about this is just first power is good enough, and we want that to be strictly less than 0. Okay, so it's a polynomial inequality. Our polynomial here, as we're getting into it, our polynomial here, good news, it's already in factor form. Okay, so it's that x minus 2 all squared times x minus 3. It's that polynomial. Okay, and so now right from this polynomial, as soon as we put our polynomial in factor form, we immediately know that there are 2 zeros for this polynomial. There are 2 zeros. One of them is at x equals -2. Okay, and I had that little typo here earlier, and I changed that to a plus sign. So that means my 0 here is at x equals -2. I have another 0 here at x equals 3, positive 3. All right, and so again, just like the earlier work, I am going to save this space of my board for the final answer. I'm going to go over there to construct my sine chart. Okay. All right, so let's now look at our sine charts. All right, so for the polynomial, it was x plus 2 squared in product with x minus 2. And then as far as the zeros from the other board, I can bring that in here and put them all into a line. So just like that, we're always going to put all of our zeros on the line from the left to the right. Okay, and so here I'm gonna go with, so how about minus 2 is the lowest one on the left, and then the next one here is x equals 3. So formally, x equals 3 is here. This is x equals negative 2 here. All right, and so now anywhere between these are the intervals. This interval here means x is less than 3 and greater than negative 2. This interval here means those x values greater than 3. This interval here means those x values less than negative 2. All right, and so now we're going to just create our charts. So here it comes the chart again. So from the left to the right, I am going to pick a value that satisfies the interval, a value for x that satisfies the interval. So in this first interval, since it reads x less than negative 2, let's pick a value, let's say negative 3. I pick negative 3. You can pick negative 4, negative 2.5 if you love decimals, negative 5. Any of those x values that less than negative 2 will work. And we'll share the same, will be the same exact result with what I have up here. So I picked negative 3. That's my choice. Okay, and so now after picking that, I'm going to substitute that into my polynomial in the product form of my polynomial. So minus 3, okay, plus 2. And then now I'm going to raise that to the square power. And then minus 3, minus 2. All right, so minus 3 plus 2 is a negative factor but squared. So that means in the next step, I'm looking at a negative factor but squared. And then minus 3 minus 2 is entirely a negative factor. So now all of that together, think about it. We're going to square this negative, making it positive. But then we're going to multiply to another negative. That gives me an overall sign. So here it has to be negative in this entire interval right there. That means my polynomial here is negative for all of the x values, for any x value. So if you choose an x equals negative 4, x equals negative 5, it turns out the same result. It will turn into the same result. So polynomial is less than 0 in that interval for x. Let's now turn our attention to an x value somewhere between negative 2 and 3. I pick x equals 0. Clearly between 2 and 3. I mean negative 2 and 3. You can choose x equals 1. You can choose x equals negative 1. Okay? So now, in my factor form, again, 0 minus, plus 2 here, and 0 minus 2. And I had a typo here the whole time. It should have been 3 here, and it should have been 3 here. Okay? And that should have also been 3 the whole time. Okay, so I sincerely apologize for that little typo, but it did not alter much of our work right there. It will sometime if I accidentally change to an x equals 2, which will make it strange a little bit. But so I corrected my typo here. So now 0 plus 2 square, well, 0 plus 2 is a positive factor, and we square that. 0 minus 3, okay, 0 minus 3 is a negative factor. Okay, so positive factor being squared is again another positive factor here, times negative. It will turn into an overall sign of being negative here. All right, so it's a negative output. So p of x, that means my polynomial has to be less than 0 here in that interval as well. So it's still being below the x-axis. in this interval, anywhere between -2 and 3. All right, and then let's move on to the last interval. So now I'm going to pick x equals 4. I picked x equals 4. You can pick x equals 5. You can pick x equals 3.5. Okay, as long as your value is greater than 3. Okay, so now in that way, let's look at that. So now, again, now I'm looking at 4, okay, plus 2, and here it's 4 minus 3. All right, and so 4 plus 2 is a positive factor, and we're going to later square that. 4 minus 3 is a positive factor. So in the end, all of these multiply together. Needless to say now at this point, it has to be a positive overall sign right there. So our polynomial here is indeed positive in this interval. Okay, positive in that interval. Okay, so now we have enough conclusion. We have enough conclusion. The question in the beginning was asking, the example at the beginning was asking, we want to find the interval or the intervals where the entire polynomial here is less than 0. And it's a strict inequality this time, less than 0. All right, so have we had our answers? Our answer is here. These two intervals together. These two intervals together is where our polynomial is below the x-axis. Below the x-axis. So now combining the interval together, let's put them together. It seems like two separate ones. So it seems like two separate ones. Somebody may write minus infinity, comma, -2. And then unions with -2, comma 3. All right, union with -2, comma 3. I agree with that, totally. All right. So here's the thing. If anyone wrote that as a combined interval, because sometimes we're a little overconfident in ourselves. So in an interval like this, somebody will question me, how come we don't put that all into one interval from minus infinity, comma 3 right there? The truth is, this interval cannot be accepted. It's not because the union is wrong, but union in this case right here, think about it, we just want the value of x that cause the polynomial to be strictly below 0. To be strictly below 0. And so now if when x equals -2 precisely, this is equals 0. This is causing a 0. This is a 0. It caused the polynomial equals 0. So we don't want to include x equals -2 here. So this is the exact answer right here. We're excluding -2. That's why this interval is not the correct interval, because it's including -2 in there. Okay, even though it seems, at first it seems logically the same, but they're not. Okay, so this is our final answer right here. All right. All right, and let's now look at the graphs of example 1, part A and B to confirm our result right there. All right, so this graph here is the graph for our polynomial in part A right there. This is the x minus 1 all cubed, times x minus 2. Okay, and with this graph we wanted to find the intervals where the graph was greater than or equal to 0. The red graph here to be above the x-axis. So now the interval shows as the results we have seen earlier. There's one interval that's anywhere from -infinity to 1 inclusively, and then anywhere from the interval from 2 to positive infinity inclusively, including 2. Okay, and so that was consistent with our result in part A earlier. And now back to zoomed out view right here. Let me now put in the graph for the polynomial in part B that we did. All right, so now this is our graph for x plus 2 all squared times x minus 3. Okay, and so now we were specifically looking for the interval of x where the graph is falling below the x-axis. So this is the portion that we particularly looking at right here. So x equals -2 is right here, and x equals 3 is right here. Okay, so those are the 0. See, x equals 3, and then x equals -2. Those are our zeros like that. So just like that, we were one interval anywhere between -infinity and -2. That's where the graph was completely below the x-axis. And then another interval between -2 and 3. That's where the graph is completely below the interval. But we had to exclude x equals -2 because x equals -2, the graph reaches to equal 0 right there, or the graph hits the x-axis. Okay, and that's confirmed our result for the example 1 in part B right there. All right, so such a fabulous skill here that we've learned in this particular lecture here, and especially throughout example 1. So let me bring up an FYT before I leave this example right here. Okay, so now we can call this an FYT right here. So let's solve about x minus 1 squared times x minus 2 cubed times x minus 4. And we want that to be greater than or equal 0. Greater than or equal to 0. So it's an FYT. Go ahead and do the sign chart as I was showing earlier. But before the sign chart, track down all of your zeros like that. Okay, I won't be showing my steps anymore in this problem like that because it's an FYT intended for your own trying like that. So go ahead and give it a try, and then I will just bring up the final answers, the final intervals, and then as well as the graph. Okay. All right. So after the sign chart there, then we should be arriving at the following the solution right here. In order to satisfy this inequality, x must be in the following intervals: minus infinity to positive 2, okay, and as a closed interval where we include 2 right here, and then we want to union with the interval anywhere from 4 to positive infinity. Okay, and so now that's our final answer. Okay, and that comes straight out from the sign chart like that. All right, and then now let me swing over to the computer and show the result from the graph right there to show the consistency between how the graph appears compared to what this is. Okay. All right, so this is the graph of our function x minus 1 all squared times x minus 2 cubed times x minus 4 right here. We had 1, 0 here at x equals 1. X equals 1, we have 1, 0. At x equals 2, we have another 0. And at x equals 4, we have another 0. Okay, and now let me zoom in even further. So, of course, this whole vertex here sinks below the x-axis. So now when I zoom in, we can just ignore the fact that it sinks below the x-axis. We're going to focus right here because this is not the part where we have to worry for. So we want to be above the x-axis. So anywhere here is above the x-axis. Anywhere above 4, x greater than 4 or x less than 2. But now this time we do want to also include these zeros here. We want to include. And so as far as the sign chart, we have the interval from minus infinity to 1. And another interval from 1 to 2. And then here is the case where we can union them together. And then we can join them together as one interval. So here we have the interval, a total combined interval from minus infinity up to 2. We include both of these points because these cause our polynomial to equal 0, which is consistent with what we were asked. And then here, this interval here, we do want to include x equals 4 because it's consistent with what we were asked. The value of the polynomial comes equal to 0 as well. All right. All right, so I'm going to bring in another example, but just one short little example just to point out, even before calculus, we are only at pre-calculus right now, but we can already see a direct application of this particular skill we've just learned here using the Sine Charge to solve for a polynomial inequality. And then in the later lectures, when we get further into our advanced understanding of these functions right here, and later even when we get into the rational functions, we will see this kind of skill again. But right here, just right after we've learned about how we solve a polynomial inequality right here, let me immediately bring up an application that's directly related to us right here. And we don't have to use many problems. We only just need to see one problem, and you will get a hang of it. So let's just say we want to find the domain. Find the domain of, so now my function here is f of x equals square root of, how about x squared minus, how about plus 6x plus 8. X squared, so square root of x squared plus 6x, okay, plus 8. X squared plus 6x plus 8, but inside the square root, and we want to find the domain of this. All right, so as far as the task of what we're doing, as far as what we need to do, it's similar kind of problems where I brought up when I was giving that lecture about finding domain and range again. But now this problem, I could not put it there back then in the earlier lecture when I was teaching about finding domain and range, because we did not learn this particular skill. Okay, so let's bring back some of that understanding we've had from that lecture about how we can find the domain and range here. In order to find it, well, this is square root. Okay, as far as the operation, this function here involves square root. And so now the domain, the only, for this function right here, and square root is the only problematic operator in this problem right here. We have no denominator. And problematic, I said, I meant something that we have to be cautious about. So from what we understood previously, then square root, anything inside the square root, right? We have an expression in the square root. Then whatever the expression here is, right? So expression, as a reminder right here, inside square root must be non-negative. Greater than or equal to 0. That expression inside square root must be greater than or equal to 0. Or in other words, whatever here, we need that expression to be greater than or equal to 0. That's the way how square root is. Square root can only take positive value or 0. That's what greater than or equal to 0 means. Okay, so directly as a consequence from this understanding. All right. So in order to find the domain here, I first started out by letting the one strict requirement for this particular problem, for this particular function here, is the x squared plus 6x plus 8 inside the square root has to be greater than or equal to 0. And just now we realized that we have produced for ourselves a polynomial inequality. Okay, a polynomial inequality. And so now in that way, now this polynomial inequality is not in factor form already. Not yet, but it's easy enough that we can put that in factor form. Okay, so this polynomial here, let's put it in factor form. X plus 2 times x plus 4. So we want that inequality, right? That we want x plus 2 times x plus 4 to be greater than or equal to 0. And we want to find the x values satisfying this, the left-hand side greater than or equal to 0. Okay, so now upon realizing that this is the polynomial inequality and we have successfully factored out our polynomial, okay, then, well, the zeros are -2 and -4. Okay, -2 and -4. And so now once again I'm going to use this space right here to write my final answer. I'm going to draw my sign chart. The sign chart is what we are about to use here. Okay, so the technique we learned in this lesson so that we can apply into the kind of problem we have seen from the past, like that. Okay. All right. So now, all right. So as far as the polynomial of concern, we're looking at p equals x plus 4 times x plus 2, and the two zeros we have found are -4 and -2. So putting them on the line of numbers, -2 is on the left. I mean -4 is on the far left. Okay, and -2 comes a little bit to the right hand side. Okay, and now this interval between here is any x, representing any x value strictly between -4 and -2, and here is for all the x values greater than -2, and this interval is for those x values less than -4. Okay, and so now once again, just like how we've been doing the sine charge here, so I'm going to pick an x value here. So less than -4 means I'm going to pick x equals -5. That's just my choice. Okay, and so now into the problem. So now I'm going to substitute the x value of my choice into the factor product. So -5 plus 4 times -5 plus 2. So this first factor would give me a negative factor. This next factor also gives me a negative factor. So in this interval, my entire polynomial, my x plus 4 in product with x plus 2 has to be positive. So it must be positive here in that interval. Okay, and now in the interval between -4 and -2, let's pick about x equals -3. Okay, it's a value between -4 and -2. So again, I'm going to produce two factors with -3 substituted in. Okay, -3 plus 4 and -3 plus 2. So -3 plus 4 is going to be a positive factor, but -3 plus 2 here is going to be a negative factor still. So in the rule of multiplication, again, positive times negative, it's going to give me a, and I should have mentioned that here, it was positive there, now it's negative here. Okay, so that means my polynomial must be negative in this interval of the x values right there. All right, and so now for this last interval, I can pick x equals 0. Simply, it's a value that I picked to satisfy this requirement. And so now I am going to go with 0 and 0, my selected value, my chosen value substituted into the factor product right here. Plus 4, plus 2, all right. And so now that gives me a positive factor here, another positive factor here. So my overall factor, my overall product here has to be a positive product right there. That means the polynomial p of x must be greater than 0 in this interval again. All right, so in that way, so now remember, our problem was an applied problem where we want to find the domain, but ultimately speaking, the domain for this function is the intervals of x, the interval or intervals of x satisfying this polynomial greater than or equal to 0. Okay, so now let's have one more look at the sign chart right here. So greater than 0 are here, those two intervals. Okay, greater than 0. So let's put them together, and then we're going to consider the inclusion a little more cautiously. Okay. And so now as far as the intervals, just to answer the intervals that meet this requirement right here, then we're going to look at one interval from -infinity to -4. Okay. And I'm not saying this is the final conclusion yet. We have another interval separate from that, being anywhere from -2, anywhere between -2 and positive infinity. We have two separate intervals, just like what the sign chart was saying. And then of course we need to union them. They are quite separate. All right, but now what about the endpoints are here? Are we including them? Okay, are we including them? Now keep in mind again, these endpoints are those zeros where it caused our polynomial to equal 0. to equal 0, and the inequality here does accept equal 0. That means we do include these endpoints in our intervals. I hope that logic of mine made sense to those who are learning from this technique right there. Okay, so now I'm going to change that to brackets here because we do want to include both of these zeros. Because again, the zeros are the values, the x values that cause our polynomial to equal 0. All right, so now this is our final domain right here. This is what that domain is in interval notation. Okay, so we use the idea of solving an inequality, a polynomial inequality, and apply that into the kind of problem where we want to find the domain of this square root function. Where we, if I taught this thing back in the earlier lecture, then we didn't have this particular skill to handle the kind of problem. All right.